This is the 7th block of Topic 12. In this lesson, we're going to be looking at similarity as a special case of congruence and look for ways to prove that two triangles are similar. So we're going to be able to recognize that we can apply properties of similar triangles to a problem situation by showing that the two triangles involved are similar. So how can you determine whether two shapes are similar or not? Remember that you can create similar shapes by defining a sequence of transformations, which include the rigid ones, known as translations, rotations, reflections, and our new transformation, dilations. So if we can have a sequence of transformations that will map one shape onto the other, then we know that those figures are similar. So look at the two triangles that are given to us. We have triangle DEF and triangle ABC. What transformations would map triangle ABC as the preimage onto triangle DEF, which is the image? So think about that for a minute. Would it be translation, rotation, reflections, dilations, or a combination of any of those? And let's answer question 1 while we're looking at this animation. So hopefully you recognize that the vertex B is going to map to vertex E. And so we definitely need to do a reflection, not a rotation, because we don't want this short side to end up on the bottom. So we want to do a reflection of triangle ABC, but also triangle ABC is larger than triangle DEF, so we also need to do a dilation. So if we do the reflection and the dilation, let's see if that is enough to get us to triangle DEF. So this is the line we're going to be reflecting over, and that creates the image of triangle ABC, A prime, B prime, C prime, and then yes, we can perform a dilation that would map that onto triangle DEF. So for your answer on question 1, can you use a sequence of transformations to determine if triangle ABC is similar to triangle DEF? The answer would be yes. We would do a reflection followed by a dilation. A reflection followed by a dilation. So, as a review, these are the shortcuts that we learned for proving triangles are congruent. So we had SSF, that if 3 sides of one triangle are congruent to 3 sides of another, that meant the triangles were congruent. We had side angle side, if we had 2 sides in the included angle that were congruent to the 2 sides in the included angle of another triangle, that meant they were congruent. ASA was 2 angles in the included side, and SAA was 2 angles and the non-included side. So those were the 4 shortcuts that would work for any triangle. Of course, we had a 5th one, HL, that worked for right triangles only. So question 2 says, how is congruence a special case of similarity? Well, if we have 2 figures that are congruent, then not only are our sides proportional to each other, they are congruent to each other, which means that proportion would have a scale factor of 1. So congruence is a special case of similarity. It's similarity with a scale factor of 1. Similarity with a scale factor of 1. So it still follows all of the same properties of similar figures in the fact that its corresponding angles have to be congruent and the corresponding sides have to be proportional. It's just the ratio is going to be a 1-to-1 ratio for congruent figures. So when we were exploring the congruence shortcuts, do you remember there were some combinations that did not work? So we had the 5 that did, or the 4 that worked for any triangle. And then we had 2 that we specifically looked at that were combinations of 3 corresponding parts being congruent, but did not prove the triangles were congruent. So remember, one of them was AAA, and one of them was the backwards cuss word, SSA. So do you think any of these would be a way that we could prove 2 triangles are similar? Even though it doesn't work for congruence, would one of them work for similarity? So we're going to first look at AAA, and we're going to see if it is a shortcut for proving whether 2 triangles are similar or not. So in our next animation, as we did with congruence, we're going to be given a triangle, and we're going to be given the 3 angles as being congruent. And so I'm not trying to, remember, make a congruent triangle. I'm trying to see if I use the same 3 angles that the given triangle has, do I make a triangle that is similar to the one that is given? So here I obviously didn't make one congruent. That's not the same size as that triangle. But if it's similar, all the corresponding angles are congruent, which they are because that's what I was using, and all the corresponding sides would have the same ratio, which makes them proportional. So do you think I made a similar figure here? Let's look at the ratios. Okay, so look at the ratios. Every single time we did get the same exact ratio. So all of the corresponding sides were proportional. Now I could do other images here, but the result's going to be the same with a different template. So answer question 3 in our notes. It says, can you construct 2 triangles in which the 3 angles of one triangle are congruent to the 3 angles of a second triangle, but the triangles are not similar? And no, that is not possible. So that means AAA is a shortcut for proving that triangles are congruent. So we don't have to prove all 6 parts again. We don't have to prove all 3 angles are congruent and all 3 sides are proportional. As long as we know the 3 angle pairs are congruent, then that's enough to say that the 2 triangles are similar. So that's what we just said, and that is called the AAA postulate, and that's for triangle similarity. Remember, AAA does not work for congruence. But we can simplify this postulate even more. Remember, by the triangle sum theorem, we said if we knew that 2 angles of one triangle were congruent to 2 angles of another, what had to be true about the third pair of angles? So remember, we said that meant the third pair also had to be congruent. So question 4, it says, suppose 2 angles of one triangle are congruent to 2 angles of another triangle. Using the triangle sum theorem, what can we conclude about the third angles in each triangle? So justifying our answer. For example, if one triangle had an angle of 30 degrees and a second angle of 50 degrees, and another triangle had the same 2 angle pairs, 30 degrees and 50 degrees. Well, what would the third angle have to be in each one of them? Remember, the 3 angles have to add up to be 180, so these add up to be 80 degrees, so the third angle would have to be 100 degrees. Well, same thing here. If I add those, that's 80 degrees. The sum has to be 180, so the third angle has to be 100 degrees. So if you know that 2 angle pairs are congruent, then you would know that the third pair would have to be congruent as well. So the third angle pair is also congruent. If you have 2 pairs congruent, the third pair is also congruent. So that means we can simplify the AAA similarity postulate to simply just state it as the AA similarity postulate. So in question 5 in your notes, it says you can simplify the excuse me, AAA postulate to just AA, since knowing 2 angle pairs are congruent is the same thing as knowing 3 angle pairs are congruent. So how might you state the AA similarity postulate? So here is our answer. The AA similarity postulate says if 2 angles of one triangle, so that's what you're writing here, if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. And you can pause this if you take a little bit longer to write that. that if two angles of one triangle are congruent to two angles of another triangle, then the two triangles must be similar. So we call this shortcut AA, not AAA. We just simplify it a little bit more. So let's look at the Sss postulate, which is another one of our shortcuts. This is number 6 that's already on your notes for you. It states that if you have all three pair of corresponding sides that are proportional to the corresponding sides of another, then the two triangles are similar. That's not the same thing as SSS for congruence. Remember, SSS for congruence said if three sides of one triangle are congruent to three sides of another. This is proportional instead. So on number 6 in your notes, I want you to underline that word proportional. That's key. That's how this SSS is different than the one that we used for congruence. If three sides of one triangle are proportional to the corresponding sides of another triangle, then the two triangles are similar. So we're proving the triangles are similar, not congruent here. Another shortcut that we have is also similarly named to one we have for congruence, and it's SAS. Now remember, for congruence, SAS meant two sides are congruent to two sides of another triangle, and their included angle is congruent. But with the Sas Similarity Postulate, it says if two sides of one triangle are proportional, underline that word proportional again, to two sides of another triangle, and it's still the included angle, just like it was for congruence, and the included angles still have to be congruent for similarity, then the two triangles are similar. So the only difference is the word proportional for the sides. That's the only difference in the two SASs. Let's look at questions 8 and 9 in our notes. So it says, how are these triangle similarity postulates useful? If you'll remember, in the overview, we were looking at a surveyor finding an unknown distance with the concept of a dilation. So suppose that surveyor creates the triangles shown in this diagram. Are the two triangles similar, and how would we know? Well, if we're looking at comparing the sides, you may think first off that you would compare the 3 feet to the 40 feet. Well, that would not make sense in this case. If you're looking for proportionality, you would always compare the shorter sides together and the longer sides together. Now, if you're trying to find a scale factor, then we typically think of the first triangle as the original one and the second one as the image. But we know in this case we were starting off with the distance in the pond, and so we were really looking at this as our original triangle and this as the image of that. So when we write a scale factor, remember that we always put the image length over the pre-image length. But again, we're going to assume the first one is the original, even though we were starting with this one. Okay, so the one on the left is always going to be your pre-image, or if they're one on top of the other, the one on top would be the pre-image. So when we're putting these distances and comparing them for our scale factor, we're going to compare the 40 from the image, since it's the longest side, to the 4 of the pre-image. So that is one of the ratios that we're going to be looking at, is 40 over 4. And then the other image length is 30, and we're comparing that to the shortest side of the other triangle, which is the 3. And so if these are proportional, then these two ratios would have to equal each other. Well, there's a couple of different ways you can see if these are truly proportional. You can reduce each fraction to see if it gets the same thing, which 40 divided by 4 is 10, and 30 divided by 3 is also 10. And yes, those are equal. Or remember, if two ratios are equal, their cross products have to be the same. 40 times 3 is 120. 30 times 4 is 120. So either way, we prove, yes, those sides are proportional to each other. Now, two proportional pairs of sides is not enough to say the triangles are similar. Remember, there's not a shortcut called SS. But in the same diagram, remember, we can always locate vertical angles when you have that intersecting lines, that like we do in this diagram, that are congruent to each other. and that is the included angle of the sides that we're looking at. So the question is, are the two triangles in the diagram similar? That answer would